This example looks at a paraboloid and a bunch of planes, 1, 2, 3, 4 different planes, and we have to try to get a visual for this so that we can do our integration properly. So let's see if we can put this on a drawing in space. This is going to be a little tricky, but we have z is equal to x, 6x squared plus 4y squared. I think in general that's an elliptical paraboloid. The cross sections are not perfect circles. They're probably ellipses, and then you can see what the ellipses are by just taking a look at these coefficients of 6 and 4. The plane x is equal to 0. When x is equal to 0, that's the yz plane. Y is equal to 3. So y is equal to 3 up here somewhere. And x equals y. What does x equals y look like? X equals y has no z in it, so it'll be like the y equals x line on the xy plane, but then it gets swept up along the z. So there we have it. So do you have a visual of this? Okay, so this is what I have so far in terms of a visual as a paraboloid. But let's see if we can visualize this without visualizing it with a picture. Let's imagine how this thing might look like. We have a paraboloid and xy plane, z is equal to 0. Okay, and it looks like this paraboloid is above the xy plane, so we're looking at some volume space between the xy plane and this paraboloid. So I think what's left to do is to take a look at what happens, the shadow that this is going to cast on the xy plane. And if we look at this shadow on the xy plane, let's draw the xy plane. We have x is equal to 0. We have y is equal to 3. And then we have x is equal to y. So I think this gives us a lot of information about the region that we're going to integrate over. And then so all we're left is to try to figure out what the integrand is going to be, and that is going to be where the z-dimensional space is being taken. So if we shade our region R or D or whatever it's called, then we can probably get this going as an integral where we're going to integrate over R, whatever that is. We'll figure that out in a minute. And now the upper z level function that we're looking at is 6x squared plus 4y squared. And then we're looking at the floor, the xy plane, the z is equal to 0 plane. And so we don't have anything else to subtract out of this. So this is going to be our general setup for our volume. From here, we have to try to figure out how we're going to integrate this. And again, we have a choice. In this particular scenario, it looks like we can choose either way. We can integrate with respect to x first or with respect to y first. Any suggestions? I would probably want to go, if I'm drawing a line here, it looks like one of the things, whenever I cross a 0, that's probably one of the things that I would prefer as one of your limits, so that when you put 0 in, a lot of that stuff disappears. So I would probably suggest that we integrate this with respect to x first. Draw a line parallel to the x-axis. And then integrate with respect to y after that. Okay, so we go into the x-axis, or we go into this region when x equals to 0. And then we're going to be in the region until we get out. And we're going to get out when x equals to y. So those are our limits. Once you got those limits out of the way, now you're in constant mode. Y goes from what to what? Y starts here at 0, and then it goes up to y is equal to 3. Okay? So let's set up our integral. By the way, I'm done doing integrals. You guys do your own integrals and stuff. In lecture, I'll set it up, and then I'll say dot, dot, dot. You guys figure it out. So the inner integral is with respect to x. We got the 6x squared plus 4y squared. The inner integral is with respect to x, so I'm going to put that x inside. And my limits with respect to x are 0 to y. And then I want to take, after I get the result of that, I'll take the integral with respect to y. And the y limits are going to go from 0 to 3. Okay? Dot, dot, dot. If you put dot, dot, dot on the test, I'm going to mark it off. I'm going to take out a special red pen.
Not red.
Can you see like dot 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 calculator solve
I don't know. We'll see.
What, I thought you were going to set up this. Oh, I thought we were going to set up the integral on the test.
Well, I haven't decided yet. You want to decide right now? I'll have you guys do it. All right, so I purposely didn't try to visualize further than this paraboloid, but if you really are a good 3D visualizer, how would you say that? If you're a good 3D visualizer, that was right, yeah. So if you're good at visualizing things in 3D, then you should really take the time to see if you can draw this out. So here's my x is equal to 0 plane that would intersect the xy plane and this graph. And then I'm going to draw my y is equal to 3 plane. Right here. And then I'm going to draw the x is equal to y plane. So if you imagine the space in between, that's the volume that you were looking for. Okay? So again, if you're a spatial visualization person, then you should really be able to visualize this, and you should, even if you're not, I think it's good practice to try to visualize things. All right, so that's one of them. Let's try another one. So there's a plane problem bounded by a bunch of planes, cylinders and planes. Let's try the cylinders and planes, number 22. So find the volume of the given solid bounded by the cylinders. Now remember that if you look at this just plainly, P-L-I-N-ly, then they look like parabolas in 2 dimensions, right? But we know that if we extend this to 3D, these are parabolas that are dragged out of whatever variable is missing, and so it really is a surface. And they're called, since these are parabola shaped, they're parabolic cylinders. So I have a z is equal to something with an x, and then y is equal to something with an x cylinder. All right, so again, I'm going to try to attempt to draw as much as I can in 3D, but our main goal is to see what the region is in 2 dimensions so that we can try this problem. So z is equal to 4x squared. So this is an x and a z. You're pretending you're on the xz plane. This is a parabola just around the origin. So kind of like this, maybe. And then if you imagine this thing being swept along the missing variable axis, which is the y, it kind of just looks like that, maybe. And then now we have y. Maybe I'll do this in a different color. Y is equal to x squared. So on the xy plane, you have y is equal to x squared. This is a parabola opening up along the y-axis. Like that, maybe. It's being swept up. Kind of hard to visualize already. And then the plane z is equal to 0. That one's easy. That's just the xy plane. And then y is equal to 4. Y is equal to 4. This is 4. Do this in green. All right, that's a little messy. Well, let's see if we can work it out. We want to find the intersection of these things. So it looks like if I was just looking at this on the xy plane, there's a couple of graphs that I would be looking for. First of all, z is equal to 0 is the xy plane, so we can think of that as the bottom of that surface that we're looking at. We have a couple of curves on the xy plane. The y is equal to x squared, and the y is equal to 4. So those two curves on the xy plane, really they're surfaces because they're getting swept up. These two curves on the xy plane look like they already define our region. And then if you imagine the other two functions, z is equal to 0, which is the floor, and z is equal to 4x squared, which is this cylindrical parabola or parabolic cylinder that we just drew, it looks like that is going to be our region or our volume. So we can keep the z's again out and saying these are going to be the integrand, the limits of the integrand, the thing that we're going to put inside of the integral, and then the y is equal to x squared and y is equal to 4 will define our region. So it looks like our volume, again, is going to be this double integral over this region that we're examining in 2 dimensions. And then we have 4x squared minus 0 dA. Now, how would you want to take the integral of this first? See? So if you go with respect to x, you're going to hit this graph at 2 different places where you have to consider plus and minus. You have to solve for x is equal to square root of y plus and minus. And so I think that's a little bit too much work and not exactly, I mean, you could do it, definitely do it, but it's not the best thing. But if you go this way with respect to y first, I think we have 2 clear functions that we're identifying as you move along your x value. So y, going from lesser to greater, will eventually go into the region when y is equal to what? X squared. So the bottom one is x squared. You're going to be inside of the region until you eventually get out of the region at this y is equal to something graph. Y is equal to 4 in this case. And how about our x? Where does our x go? So they intersect here at positive and negative 2, right? So from negative 2 to 2 are your constant outer limits. So now we have a setup. Our inner integral, 4x squared is our integrand. We're going to integrate with respect to y first from x squared to 4. And your outer limits with respect to x, outer limits are always constants, negative 2 to 2. Okay? All right, now, just for the sake of visualization, I didn't quite finish visualizing this. But let's see if we could extend this a little bit further because one of the cylinders could have gone farther out. So we have this block over here that would stop the cylinder from going any further. Now, the blue graph kind of provides the boundary and the x the green graph over here will provide the shape. So on the front, if you're looking at the view that we're looking at, on the front over here, we have this. This is kind of curved over here, and it's curved with respect to this black graph over here, because this graph is this cylinder z is equal to 4x squared. And then we cover it in the front with this green plane. And this is the only bit that we're going to see in the green plane. And then that blue cylinder over here, that should be blue, is going to cover that up. So this is a strange looking shape. But this is going to be your volume. Can you guys visualize this? This is really hard to visualize. All right, let's do some more. Planes, first octant, cylinders, planes, cylinders. All right, here's an interesting one. Let's do one where you might need to change your perspective a little bit. Volumes of two, wait. Find the volume of the solid by subtracting two volumes. The solid enclosed by the parabolic cylinder and the planes. What are you subtracting? I don't like that problem. Let's try another one. Well, I kind of took that a little bit differently. Subtracting two volumes, the volume enclosed by this parabolic cylinder and the planes, this and this. So I think I see two planes and then a parabolic cylinder is going to be your boundary. But I don't know. I suppose we should do it since now we're making a big deal out of it. This might be a good one after all. So our initial sketch in 3D will be on a parabolic cylinder. So again, it's a cylinder that looks like it's opening along the y-axis. And then now we have two other functions. Z is equal to 3y. Let me see. That's on the y and z plane. And this has a slope of 3, so it's fairly steep. And z is equal to 2 minus y. So I see that as a positive slope. 2 maybe I should use a different color. 2, slope of 1 instead of 3. Wow, this looks crazy. Probably too much, huh? So there's a space in between these two planes and this cylinder. So I guess the question I have is, where are these two cylinders, where is that space going to close up? Can you guys picture this? I can't use my picture anymore. It just got too convoluted. So let's see if we can graph it. Soda.
Maybe an extra point on the quiz.
Jinx, you owe me an extra point on the quiz?
Yeah. Should it become a thing? We all start guessing what you're about to say. And if we get it right, we get an extra point on the quiz.
That's interesting. So, you guys can actually see this clearer now. Well, kind of. All right, so it looks like we might need to zoom in. Let's stop this for a moment. So we got this parabolic cylinder, and somewhere over here, these two graphs are intersecting. So I wanted to take a little peek over here. This little space. This is one plane, this is another plane, and there's a little space over here that's enclosed by this big cylindrical or parabolic cylinder. This plane up on top and this plane down in the bottom. You see that? So that is the little enclosure that we want to get. Now the problem is, let's see if we can visualize the problem. So it looks like if I was going to integrate this, I think my planes are going to be the top and bottom limits of my integrand. Maybe I shouldn't say limits. Maybe they should be my my integrand. And if I could just figure out which one was on top and which one was on the bottom, then that would be good. It looks like the green one was on top. Which one was the green one? This is the green one. And then this is the higher of the two planes, and this is the lower of the two planes. And they do intersect somewhere over here. I'm going to want to figure out that intersection. And it looks like this was in black. It looks like this is going to end up being the boundary that we have on the XY plane. So again, this is still not the type of problem I wanted to do, but we're here, so let's just finish it. So we got the y is equal to 16x squared graph. Now it looks like they're going to eventually meet over here and get cut off over there. So the question is, what is that y value where they get cut off? And what happens is that the blue and the green planes look like they intersect up here. So how would you propose we can find the intersection of the blue and the green planes? Whenever we find intersections, we have to, quote, set them equal to each other. Now that takes different contexts, different ways of setting things equal to each other, But this one seems pretty straightforward. We have z is equal to something and z is equal to something. So what if we set them equal to each other, like 3y is equal to 2 plus y. So what's y equal to? 1? Wow. So y is equal to 1 is going to be our intersection. And so we have a well-defined region now. Okay? And we know we're going to integrate with respect to y first and then x, right? But I guess a more interesting part of this problem, aside from figuring out how to integrate with respect to first, is the fact that you have an upper and lower function, right? The two planes provide your upper and lower function. So it looks like the upper function is going to be the green plane, 2 minus or plus y, and then the lower will be your blue plane, which is 3y. Okay? All right, all these examples bring things back down to y, and I was looking for examples, or bring things back down to x and y. I was looking for examples where we might have to integrate with respect to x and z, but I think that's going to come later on. So if we're good with this, I want to move on to another problem, another type of problem in our last 2 minutes. And there's some other visualization here that I think that's going to be important for you to do. So let's take a look at this problem. This is one of my favorite problems, and I pretty much guarantee that one of these will pop up on the test. Instead of giving you a scenario where you have to try to visualize and set up your integral, here you already have an integral. But if you were to attempt this integral, to do it straightforward, you're going to get stuck. Turns out that we don't have an integral for e to the x squared. Another approach to this problem might be to switch the order of integration. So let's take that plan and switch the order of integration. So we kind of have to work backwards here. So we're going to work backwards by using those set of inequalities like we've had before. And so what we're going to do is realize that the inner integral is with respect to x, the outer integral is with respect to y. Once you do that, everything else should flow quite easily. So the lower limit for x is 3y. The upper limit for x is 9. And then y goes from 0 to 3. Okay? Now, oh, by the way, I should have done this incorrectly first. This is the really, really naive, incorrect way of doing this. Why is this wrong? Outer limits have to be constants. There's a 3y here, not a constant. That is bad. So, now that you know what to do, you would graph this. X is equal to 3y. What's x is equal to 3y? That's like y is equal to 1/3 x, right? Fairly low slope. X is equal to 9. Going from 0 to 3. So you can identify your region, and then now work forward again. So we're kind of at the integral stage. We work back to get our region. Now let's go forward, but this time, instead of integrating with respect to x first, let's integrate with respect to y. With respect to y, a line parallel to the y-axis, you're into the region at y is equal to 0. You're out of the region at y is equal to 1/3 x if you solve for y. Constant limits going from 0 to 9. And now you might have a fighting chance in doing this integral. With respect to y first, from 0 to 1/3 x, and then with respect to x, from 0 to 9. So explain why this is doable and the first integral was not. Oh, constants are outside. But I'm talking about this integrand. Explain why we can do this integral now, but we couldn't before. You're integrating. Yeah, you're integrating with respect to y, so this is constant. So this is going to have some y in it, and then you're going to replace it with x. And then now your second integral will have an x in it, and you can do a u substitution. Okay? All right, this is doable, and the other one was not. So that would be a good reason to switch the order of integration. So you need to know how to switch the order of integration. Okay, next time, polar coordinates. It'll be fun. What? Yeah, I think so. All right, see you guys on Monday.